tell you something about the theory behind expectation maximization methods. We need one preliminary, Jensens inequality. In one dimension, Jensens inequality is pretty simple to see. It says that if you have a function which is concave downward, such as the black function I'm showing here, and you interpolate its values between any 2 points that lie on the function, for example, this one and this one. So an interpolation would be any point along the red line here, linearly connecting them, and the interpolated function value would be here. But as you see, the true function value, because the function is concave downward, is always higher here. So Jensens inequality in this case says that the function of the interpolation, that would say up here, is always greater or equal to the interpolation of the function here. Now, this interpolation is a weighted average between 2 points. But Jensens inequality is also true if you have a weighted average of multiple values. So here's Jensens inequality applied to the logarithm function, log, which is shown here, which you can see is concave downward. The second derivative is everywhere negative. So Jensens inequality says if we have a set of weights lambda I, which add up to 1, so that they're the kind of weights that you might use in an interpolation, then the log of the interpolation, that is to say the weighted sum of some values qi, is always greater or equal to the interpolation, the weighted sum with the lambdas, of the logs of the individual values qi. This gets used a lot when we're playing around with log likelihoods, as you're going to see, and it gets used in the proof of the EM method that we're now going to give as one example. So here's the basic EM theorem that's due to Dempster, Laird, and Rubin. We have some set of data, x, bold-faced as a vector. And then we also have some set of missing data, z, but z can also represent nuisance variables in the fit. So actually we're going to get two theorems here for the price of one. It's the same theorem, but you can interpret it in two different ways, depending on whether you want to view z as missing data analogous to x, or nuisance variables in the parameters in the fit analogous to here, the third thing we've got, theta, which are the parameters that we're interested in. Now what we want to do as always is we want to find the values of the parameter theta that maximizes the log likelihood, that is to say the likelihood of the data. So this is one of these proofs that if you do it in the forward direction, the steps seem unmotivated. How did anybody ever know to do that manipulation? And it's only after you arrive at the end, and if you think about it a while, you'll see how somebody could have kind of worked from both ends and figured this out originally, as was done by Dempster, Laird, and Rubin. So we start with this function L of theta that we want to maximize, and it's defined as being the log of the probability of the data given the parameters theta. And we want to maximize that over theta to find the maximum likelihood parameters. First step, rewrite this marginalized over the missing data z. That is to say, we sum over all possibilities of the missing data, probability of x given now z and theta times the probability of z given theta. So this is an equality just by the laws of probability. Now here's the sort of mystical step here. You'll notice that this term simply comes down to here, and this factor, I should say, comes down to here. And now I'm going to multiply and divide, so I haven't really changed anything, by this funny thing. This is the probability of the missing data given the data that we see, but it's not evaluated at the same value of the parameters theta. It's evaluated at just some random new value of parameters theta prime, and we'll see why that's an important thing to do in a minute. And then over here, I've added and subtracted something else. I've added and subtracted basically the this L function at theta prime, and by its definition up here, I can write it also in this form when I subtract it. So why do I do this strange manipulation? It's so that I can now collect the terms and use Jensens inequality here on the log of the sum over z. Okay, so I can bring the log all the way into here, because basically these p of z's given x and theta prime play the role of the lambdas in Jensens equality. They play the role of the weight functions. Okay, and so Jensens equality lets me move the log into here. Now the reason that I generated this little term here was so that I could move it into the log and make this thing look more symmetrical. And in particular, you'll see that we have two contingent probabilities, which by the laws of probability simply become down here the probability of xz given theta, and the probability of zx, which is the same as xz, x and z, given theta prime. In other words, what I've been aiming at is to get this nice term in here, which is a log odds ratio. It's a ratio of probabilities between all the data seen and missing at parameter value theta and all the data seen and missing at parameter value theta prime. Now, you still may not be able to see where we're going until the next slide, but let's just define this whole thing here as a function of two variables. It's a function of theta and theta prime. In other words, it's a function in two different guesses for what the parameters may be. And the trick is going to be that we can kind of leapfrog between these two arguments to get an iterative method. Now notice that if I set theta equal to theta prime, then this becomes 1, the log of 1 is 0, and this b function, which I think I was circling it wrong just a second ago, it includes all of these terms up here. This b function then becomes exactly equal to L of theta prime. Also notice that because of Jensens inequality, this function b of theta theta prime is always a lower bound to L of theta. So how do we put that all together? This is what I've just said. At theta equals theta prime, we have that L of theta is equal to L of theta prime, obviously, and our bound b, which is here drawn, touches the likelihood, the true likelihood function L of theta. Okay, so the idea now is that we start off setting theta prime, I should say setting theta equal to some guess theta prime. Then we compute the b function. We know that the true likelihood function at that value of theta prime has the same value. Now we maximize the b function over theta. Now we could either do that locally, ending up here, or as I've shown here, we might be lucky enough to have some way of doing it globally, ending up here. And that's our new guess, theta double prime. And what do we know about that guess? Well, we know that the true likelihood function is even greater in value than the b function that we've just maximized. And we also know that the value that we just found here by maximizing b was greater than the starting value of b here by definition of maximize. So that we're guaranteed that this step from theta to theta prime has increased the overall likelihood of the model. Now how can this terminate? If you think about it, you'll see that this can only terminate at a maximum of the true likelihood. It might be only a local maximum. We can hope that it will be a global maximum. And why is that the case? Can you see why? Well, it all hinges on the nature of this tangency point here. When we set theta equal to theta prime, we find that the values are the same. But it must also be that the derivatives are the same and that there's a tangency. Otherwise, the red curve would cross the black curve if the derivatives didn't match. And that's ruled out because the red curve is always a lower bound to the black curve. So we're guaranteed that each step of EM increases the overall likelihood, and we're guaranteed that this can terminate only on a at least local max of the likelihood, the log likelihood function. And it works whether we actually use a local or a global maximizer when we're working on the red curve. So let's go back to the equations. The general EM algorithm, therefore, simply repeats this maximization problem. It says, find a new value theta double prime that is related to your starting value theta prime that occurs here and here by being the value of theta, argmax, that maximizes this expression. Now we can rewrite this in an interesting way. Notice that we're maximizing over theta, and that if we expand this log into the sum of two terms, that is to say the log of this minus the log of this, the piece that's the log of this doesn't contain a theta, and it's multiplying something here that doesn't contain a theta, so it's simply irrelevant to the maximization. So therefore, this same argmax theta double prime will be the argmax of this problem, in which I can simply cross out that denominator. Now another rewriting of this is sometimes useful in its own right, but another useful rewriting is simply to use the law of conditional probabilities and write this out as being the probability of x given z in theta times the probability of z given theta. Now let's stand back and look at this, because now we can finally see why the EM algorithm is called the EM algorithm. The E step here is computing the expectation of a certain quantity, this log inside, over a certain probability distribution. And here's the probability distribution that we need. It's the probability of the missing data given the data that we see and given some guess as to the value of the parameters. So that's the E step. The M step for maximization is this outer argmax over theta, and maximizing this is the M step. Now, it looks like this is a difficult operation because, after all, this is some kind of big sum or big integral over a probability. And a lot of the power of EM methods come from the fact that there's sometimes, for particular problems, not in general, a tricky way of doing this expectation that's better than literally trying to integrate over all of the possibilities of z. So that's something to keep in mind. Also worth keeping in mind is that when we've written out this conditional probability in this way, then in particular problems there are often simplifications. For example, if we're dealing with a missing data problem, so that z are data points that just somehow we forgot to measure and x are the data points that we measured, then if each data point is independent of the others, there'll be no dependence, no conditionality of x on z. And so we can cross out the z here, and we'll simply have what our model tells us about what is the probability of x given the parameters of the model. Another simplification occurs when we're viewing z as being a set of nuisance parameters, in other words, an augmentation to the theta vector, but just some parameters that we're not interested in. Because often then we can assume a prior on those nuisance parameters that's uniform when it's conditioned on the other set of parameters. In other words, if the parameters have priors that are independent of each other, then this thing can just be 1, and we can cross it out of the equation. So what we have here is a very general way of handling, as I say, we've got two theorems for the price of one, of handling either missing data, where you have a set of data points that you've measured, and there's some other set of data points that you wish you had measured, but that you forgot to measure, and you want to estimate statistically what their values are. That's the missing data problem. And it's also a very general way of handling the nuisance parameter problem, where you're trying to estimate some parameters theta, but in order to get the whole model, you have to include some other parameters z that you're just not interested in and you want to marginalize over. Now, we got into this whole subject by doing Gaussian mixture models. And it may not be instantly obvious to you how a Gaussian mixture model fits this paradigm, but it does. For a Gaussian mixture model, the trick is that z, the missing parameters, are the assignments of the data points to the components, whereas the parameters themselves, theta, are the means and covariance matrices of the Gaussian components. So if you think of it that way, you'll see that this thing that we marginalize over, this probability of the assignments given the data, is just this thing which in the previous two segments we called the matrix Pnk. That's the probability that each point n is assigned to any component k. And the marginalization, I should say, the expectation over this is just going to be a weighted sum over the elements of this matrix. In fact, what is that weighted sum going to be? Well, it's going to be here. This is the expectation piece of the E step, and then this is the thing we're trying to take the expectation of. This is an example where the extra term inside the log, which was a probability of z, now a probability of assignment, can have a prior which is uniform. Therefore, we don't have to put anything extra in here for its prior. So now the log of the probability of a data point lying at position x, given the parameters of the model, is just the log of the probability of the data in a particular Gaussian. Why just one of the Gaussians? Because here is where we're taking the expectation over the different possible assignments z. And the log of the probability of a single Gaussian is just this familiar thing where this looks like that thing in the exponential of the Gaussian, and this is that thing that lies outside that takes care of the normalization. Well, this still doesn't look easy, because now the maximization step says that we have to maximize this thing over all possible values of the means of the different Gaussians and all possible values of the covariance matrix of the different Gaussians. And you might think that's a really hard problem. But I want to remind you that all the way back in segment 7, when we were talking about measures of central tendency, and in just the one-dimensional case, we proved a little theorem that the way you maximize the likelihood of the mean of a Gaussian is just you take the population average. You just take the points that you're given and you average their location, and that's the best estimate of the center of the Gaussian. And we saw that the way to find the maximum likelihood estimate of the variance of a Gaussian is just to take the sample average. I might have said population before, but I meant sample average of the data that you have. Now, the same goes through in multi-dimensions. So there's a fancier theorem that says that the maximum likelihood estimate of the multi-dimensional mean of a set of points drawn from a Gaussian is just their multi-dimensional average, and similarly for the maximum likelihood estimate of the whole covariance matrix. If you want to see this derived, then there's a nice article in Wikipedia under the expectation maximization algorithm. So this has been a very general treatment of EM methods, but we're going to see them again in some practical applications later on when we discuss hidden Markov models. And the so-called Baum-Welsh re-estimation algorithm for hidden Markov models is very directly an EM methods. There are all kinds of other EM methods around, and every once in a while you have a problem which has this general character. If I knew A, whatever A is, then I would know B. Oh, but if I knew B, then I would know A. And in cases like that, you can often figure out that what you've got is a estimation maximization problem, and you can rely on the EM theorem to prove the convergence of an iterative method where you go back and forth between the A's and the B's.